we'd like to welcome Catalina Albornoz from Xanadu. This is the second part in the QML lecture series with Womanium Quantum Program and Xanadu. If you are watching this session on YouTube as a recording, I would suggest going back to the previous lecture by Catalina on QML, just so you are in sync with whatever has been already discussed. And then we move on to today's session. Over to you, Catalina. Please introduce yourself and then start with the session.
First, thank you. I forgot to open the Discord, so maybe you can help me out with the questions and interaction. So for everybody, it's great to see you again. This is also going to be an interactive session. If you're here for last time, maybe give me a reaction if you're here, or for whoever's on Discord, you can let me know, Vardaan. We're getting the reactions. Did people participate last time in part 1? Or did anybody not participate in part 1? That's okay. Just let me know. So give me some reactions if you're here on Zoom. Any reaction works. Yes, I'm getting the reactions. Perfect. All right. Awesome. So today we're going to focus on some more advanced topics. First, let me introduce myself. Yes, I'm Catalina. I work at Xanadu. So I guess if you've already been here, you know me already. I work with the community, building the community for Penny Lane and Xanadu in general. So I'm going to do a very quick recap, and I'm going to focus more on hybrid models, QNNs, and quantum kernels. We're going to show a little bit of code to see, how this looks in practice, and again, going to show the resources where you can keep practicing. So first, this short recap. Quantum machine learning models, they're different, they say machine learning, and they share some of the same ideas and techniques that we have developed over so many years in classical machine learning. But we have to think about them in a different way, in a new way. Not everything that works in classical machine learning should work in quantum machine learning. And so the big question that we're tackling, and like the question in the field, is what problems are actually well suited for quantum machine learning? What problems can we solve with this? It's not there's not a set answer, right? Yet. We're figuring it out. In the meantime, this is why it's very important to understand the fundamentals, how this works, how you can build it, how you can test it. And especially we're going to focus in the last session on critical thinking about it, like what doesn't work here as well. So what we see here in the first image is a quantum circuit. You first have an embedding, then you have some parameterized layers. Usually they're parameterized layers. And automatically, through the way we do the optimization and the training, we're going to find the best alpha and beta that will find the lowest value of my cost function. We generally want to minimize or maximize something. So maybe we can find the lowest energy in a molecule, or maximize profits for a company, right? Of course, this is maybe far away into the future. But we're generally going to think about these cost functions. We're not going to be able to see them, plot them, because they're going to be very complex. But we're going to use optimization in order to find those minima. And if you actually wanted the maximum, there's a tiny mathematical trick. You just add a minus sign when you do the optimization, and that's it. So quantum machine learning models, we're using quantum circuits, we're changing the parameters, and we're using different optimization methods. In this case, in the right-hand side, we have a gradient-based method, but there could be other methods. And we're gonna use them together with classical. So we're not gonna use this on our own. We're gonna use this together with classical. This is like the general idea. So some concepts that we saw last time, encodings or embeddings, that's this first layer that we see here in orange. What we do is we start with a 0 state. We always start with a 0 state because, we have to reset our quantum computer to something, that we know, that is for sure. So we're going to start with a 0 state. And then we're going to have our data. In this case, there are angles, pi over 4, pi over 3, pi over something. And we're going to embed them into our quantum circuit. Now, once we embed them into our quantum circuit, and there are many techniques for these. Last time we saw 3 options, but there are many others, and there's not a set one that will work always. So you will need to decide what is best for your data so that the data will be separated into clearly distinct quantum states so that, you can actually work with them independently and the circuit will understand how to treat this data. Now, after that, you will have often a number of layers. And so these can be like the classical, like you can find the classical reference in neural networks where you have a number of layers with some parameters that you're going to train. So this is kind of the same framework or way of thinking that we've brought from the classical, classical machine learning. So here we have 2 parameterized layers, layer 0 and layer 1. And together this second part of the circuit becomes our ansatz. So our ansatz is basically that layout of the circuit without really caring about what specific angles we have here, what specific parameters. We're just like making the architecture plan, the architecture map of what this circuit is going to look like. So that's our ansatz. It's our guess of what is the layout of the circuit, what it should be, not caring too much about the specific parameters. So this can actually change. For example, let's say it turns out that upon training, theta 1 and theta 2 become 0. So basically that means these gates disappear. That is possible. So our ansatz is just this basic layout, but that the actual implementation of it, depending, after we do our training, could actually be different. So, and at the end, so we can have many different layers, and each layer you can have, like, say, this one, we can call it layer B, A, and the second one can be layer B. And we can then interchange them and have a number of these different layers. And at the end, we will have a measurement. And our measurements, we often use expectation values. Expectation values are like an average taking over, we can imagine a very high number of samples. So you have maybe seen shots, right? An expectation value is taking an average over a certain number of shots. If we don't specify the number of shots, we can think there are a lot of them. You can think of infinite shots. Of course, that is not possible. But you can think of it this way, saying like, it's the average if I had ran this many, many times. So our expectation value is going to be a very useful number that we're going to find and use in so many of our algorithms. There are other options. You could use probabilities. You could use samples again. But expectation values are kind of this nice average. Now, we're perfect. We've done our recap. Are there any questions about the recap? Did somebody maybe have additional questions that we didn't get to cover before?
Yeah, one quick question, Catalina.
Yes.
About the ansatz, is there a way where the participants can find guided structure on how they can create ansatz for a specific problem, or is it only on a trial and testing basis that they come up with the best ansatz?
Usually you would start, depending on your problem, you would start with who else has done something similar and what ansatz they have used. So there are some, let's say, generic ones. So there are some which just add a lot of random gates. So that's an ansatz, and there are templates within Penny Lane. And I can go to the website and show you to the documentation and show you where you can find some examples. So there's one option which is a lot of random stuff. And this is a good way if you're doing, for example, benchmarking. You don't want to only benchmark for something specific. Sometimes you want just a lot of random stuff. One other option, which is very, very often used, is strongly entangling layers. So when you want a lot of entanglement, we know how useful entanglement is in quantum computing. And so you can have an ansatz that creates, one layer, one parameterized layer, and then entanglement, and one parameterized layer, and then entanglement. So this would be something like a strongly entangling layers ansatz, and you have as many of these layers as you want. You have an ansatz that is more like for QAOA. So I can show you the place where you can find different templates. I would say I generally use strongly entangling layers just as a default because it's easy and it creates a lot of entanglement, which is generally good. But it will depend, because if you, for example, have a very, very big circuit, this is going to be hard to run. This is going to be like heavy to run. So if you want something that is more lightweight, maybe you'll need to choose something that doesn't have as much entanglement, which can have its cons in general, but if you know your problem, maybe you can tweak it. So my recommendation, just in short, is look to what others have done and start with trying to replicate what they have done to see if you get the same result. And then you can try, if you have a better insight of the problem, for example, if I knew that this last layer you didn't need so much entanglement between all of these layers, maybe I could remove some of these. And then this is my way of modifying that ansatz with problem-specific information. Or again, looking at another technique that you want to combine here. So this is something that you can do. For example, if you want to do circuit cutting, this is something that helps you reduce RAM, like memory, and help you run bigger circuits on smaller devices. I would, for example, remove this almost last CNOT, because that would make it easier to split the circuit into two. If I make a cut here, right now I still get this connection here. So I could just make one cut here. If this didn't exist, I could make one cut and split the circuit in two, and then run the two individual parts in smaller devices. This is some way that, knowing exactly what I want to do can help me change the ansatz from whatever the base is. I know it's a very long answer, but hopefully it gives you some more clarity.
Perfect. Yeah, I don't see any more questions. So yeah, we can move forward.
Great. So hybrid models, it's very useful because we're not going to do quantum on a vacuum, right? So, I mean, literally, yes, but we're not going to work together, just quantum alone. We're going to work together with classical. And so hybrid models become very important because and parts of your computation on one or more quantum computers, and then combine those answers with classical processing or classical neural networks, and then found an answer together. So this is going to be this is a key thing. You're not going to do your quantum computations on your own. And the way that you combine them, there are so many different ways that you combine them. So doing classical computation has a lot of different challenges. One, you need to make sure that the information can be plugged into, the different layers in a reasonable way. So let's look at the image that we have on the right. We have a quantum circuit. It's running on a gate-based model. You have some input, right? This can be and encoding the data. This could be encoding data. For example, if you just have one layer, I know that it's tiny, but you can imagine you're just encoding some data here. And now you're measuring two outputs. So what do you do with that? You can decide, and this you can decide in your program, how you're going to manage this. You can decide that the first output of the first qubit, you're going to add them up. And the second output for the last qubit, you're going to calculate the sign function of that. So how we process that data, it doesn't have to be all sequential in a line. And we're going to see that. You can actually split it into pieces and recombine it in different ways. And maybe even put it back into a quantum circuit. So for example, here in the picture, after the sign function, we're plugging that back into a different quantum computer. And then we're again getting an output, which we're modifying classically. And finally, we're just adding them up to get one single output. So this is one way of how you can imagine a hybrid model working. You don't do everything in quantum or everything in classical. You combine them in the better way possible, and quantum kernels are an example of that, and we're going to see that in a bit. So here we have a sequential model. Here it's an example thinking of torch, so this is why you see torch layer. If you're deciding between, for example, torch or keras or JAX, or something else, I would generally recommend torch or JAX, like they're more widely used and more compatible. So I generally would recommend torch or JAX. Or there are some like other alternatives. For example, we're developing a hybrid compiler, which is called Catalyst, which works a little bit like JAX. But if you're, you have your classical machine learning model, I would recommend generally using torch or JAX. So let me know, give me a reaction if you have used classical machine learning before. Give me a reaction, a thumbs up, or any reaction. Yes. All right. So you probably are used to this idea that you have, oh, no, not everybody. Okay. So for those of you who do not have any classical machine learning experience, I would absolutely, it's very worth it to try to get some of that classical experience. It will help you understand the notation better, the concepts, and you can combine them better. So you don't have to think that, you have to forget about all of your classical knowledge. It's going to be very useful. So here we have a hybrid neural network. And in general, something that is very important to note is that quantum neural networks, that same concept is sometimes even problematic for people, because just the quantum circuit, even though it has some components and concepts that can sound similar, the inner workings and the way you can handle them are different. So here we're going to talk about a hybrid neural network, but with the important caveat, and this is very important, that you cannot just assume that everything that works in classical will work in quantum, or that it will work better. Often it will be worse. So here we have an example. So we have some input data, which we're first passing into a classical layer. So the way that these classical layers work is that you add, you have some weights here in your different nodes, and you're going to have a forward pass, meaning that you're going to go from left to right. You're going to calculate the output. So here we have some input data. I have my input data separated into a number of neurons here too. They have some weights, so they're going to be combined with a specific, some specific weights. And here, these two, the outputs, it looks like just one line, but they're actually two outputs here of my classical layer. They're going to go into my embedding part of my quantum circuit. So I'm going to put the output of my classical layer, and it's going to become the input of my torch or my circuit. In this case, we can use helper functions, but you can program this in any language that you want, probably. There are many that have these combinations. Catalina just makes it easier for you so that you can embed that data directly, into the first layer of your quantum circuit. Then you can have your parameterized layers. You can have your, variational algorithm where you have different parameters. And now then you have a measurement, and you can decide how many outputs you're going to measure. And this is going to be very important again, because if you decide to measure all of the outputs, you have to make sure that this matches the input of the next layer. So if you're just going to measure one output, one qubit, you're going to make sure that that matches the input for the next layer. Here, we're measuring all of the outputs. So we have two outputs. That's going to be input into my next or last classical layer. It's going to take two inputs, and it's going to output one single output. So it uses a classical softmax in order to just give me one single output here. So this is what a sequential model looks. You have your quantum component into a hybrid model. This is what a non-sequential model would look. So you can actually choose, and again, this is similar to the example that I showed before with the yellow and green boxes. In this case, we have a classical layer, and we're not gonna put it all together into one quantum circuit. We're gonna split it into two. So this requires a little bit more work, but it's definitely possible to do. And you're gonna embed the outputs of that first layer in two in the first quantum circuit and two in the second quantum circuit. And at the end, you're gonna need to combine the outputs of your quantum circuits in a smart way so that you can actually input it into your final classical layer. So you have to be very careful about how you manage the dimensions here, so that everything matches. That is the most common error or like confusion that I see is, I'm going to change the data set and this no longer works. It's because very often the sizes don't match, right? Or I'm going to make a bigger quantum circuit here. Often the sizes won't match with whatever layers you've quoted before. So this is something that you can have in mind about how to combine, how to plug and play these these neural nets. Now, quantum kernels, they are they're a very popular thing. Like they had a lot of like they were very, very popular because it helped with one part of the computation that was very, very hard for classical computers. Is what if your data, for example, you want to classify it, you want to split it in two. What if it's not separable? So if I asked you for the diagram in the left, show me a straight line that will put the red axis on one side and the blue axis on the other side. So is there any one single straight line that you can draw here? No, the answer is no. And so what do we do with these problems? We can do something here like a feature map, which means we're going to take our features, our data, and we're going to map it into different parts of the space. So instead of having it all like, be clumped one around the other, we could decide, for example, to apply a certain transformation so that for all of the red dots, they're actually going to go, let's say they're going to be multiplied by a smaller number or something. And for all of the blue dots, they're going to be multiplied by a larger number, something like this. And then you can actually find a line where you can split that data. So this is not as easy as that, because when you get a new data point, you actually don't know what class it belongs to. Quantum computers help you do that just by the fact that when you input your classical data into your quantum circuit, you're actually putting it into a space that has more dimensions. So if you have n qubits, if you remember your probability amplitudes, you have your state vector. Who remembers the state vectors here? Actually, give me a reaction. Who remembers, the probability amplitudes in your state vector? Yeah? Okay. Good. So that is, alpha times 0 plus beta times the 1. Your alpha and beta are your probability amplitudes. And actually, when you have many qubits, you have, alpha times your 0, 0 plus beta times your 1, 1, and, beta times 0, 1, and gamma times 1, 0, and so on. So you actually have 2 to the n of these probability amplitudes. So 2 to the n is way bigger than just n, right? So 2 to the n, well, it depends on n, but 2 to the n scales much more. So you're saying that you have a higher dimensional feature space. And so what you see in the top right diagram is representing that. So instead of having just your data all clumped one around the other, when you map it into a space that has more dimensions, you actually, it makes it easier to find those planes or those lines where you can distinguish one group from the other. And this is for classification, but it can work for other things as well. So let me know how we're doing with quantum kernels so far. This is so far the part about a feature map. So you're mapping your features into a new space. So you can think of in cartography, let's say you're talking about the world is round, but when you make a map, you're mapping it into a plane. Here it's like having the reverse. You have your map of the world on a plane, and you're mapping it into a globe, into a sphere. It's not always a sphere, it's something with more dimensions, but it can give you an insight of why these feature maps have value and why they're important. And our quantum computers, by the fact that they have, this higher dimensional feature space, then it can be useful to map those things there. So let me know how we're doing with quantum kernels, or should we go back and review a little bit? Yes, give me some reactions, or let me know how we're doing on Discord, Vardaan.
Yes, I think we're good.
Yeah?
Yep.
Good. It's sometimes useful to see this in a graphical way and think about it. You can think of the example of, the globe and the flat map, and how you can actually do more fun things when you're seeing things in a higher dimensional feature space. Now, this is gonna be a little bit of math, but it's just to show I learned with math. I can understand it. It helps me understand. So I hope it will help some of you. If you don't understand it, just let me know. So what we have here is an equation for a support vector machine. So what we had in our previous slide, here at the bottom right, was kind of what we have with a support vector machine, which is a classical way of separating data. Basically, it's finding this line that will separate your data. So you have an equation in the middle here that says, if you have your data and your data is X, you're gonna want to find the vector W that can will help you classify whether something is up of the line or down of the line. So you're gonna want to find this line, and then you're gonna be able to classify whether something is perpendicular to the right or to the left. And so what happens when you map something? So this this phi here, which is this feature map. When you have this feature map, what you're gonna find is that in your normal equation that you had for your support vector machine, you have two phi's here. So for two data points, xi and xj, so x is your data, so for two data points, xi and xj, you're gonna have to find the inner product of these two vectors, basically. And that is what is going to become your kernel. So far, this was just feature map, but the kernel is basically this little part, this multiplication, which is now going to be called K. So on the right-hand side, you see we've called this multiplication of phi of xi and xj into K of xi and xj. So this multiplication is going to be called our kernel. And it turns out that we can code this into a quantum computer without even needing to keep doing the training for that data set. So what we have here at the bottom is an example of that. You start with a 0 state. You then make an encoding. So you can make, for example, an angle embedding. And here you're multiplying it by the adjoint. And then you're going to measure on a specific projector, which is basically you're projecting back into your initial state. And you're getting this measurement. So basically, you're calculating this complicated part of your classical, let's say this was part of your classical function, but you're actually going to run this part as a kernel that runs in your quantum computer. And so if you look at the code, And let me go back to the basics of what we're doing here. We're first creating a device. Our device is our backend. It's wherever we're gonna run our quantum circuit. Okay, actually, yeah. Does anybody need a recap on how to program? Maybe? Yeah, I think we need a recap. Okay, so we're gonna first create a device. In this case, we're gonna use a simulator. It's called Lightning Qubit with a certain number of qubits. And this is gonna basically say, I'm gonna run on the specific backend or device. We're not gonna think about the projector for now. That's gonna happen at the end. We're gonna think about this at QML.QNode. This line where we assign a specific device to the circuit that we're gonna run. And the circuit is gonna be the function that is right below. So our function is going to be our kernel, which takes 2 data points, 2 inputs. And we're gonna find that inner product between them. We're gonna first do the embedding, angle embedding of x1. And then we're gonna find the adjoint, so this is like the complex conjugate of that, but applied to x2. And this is gonna give us that inner product. And what we're gonna do is we're gonna measure that inner product with respect to a specific, to the initial state. This is our initial state, which is our projector. So if we go back, if we go back here at the bottom, we're gonna see that we're going to measure, basically mapping back into that initial state that we have. So that's what we're doing at the end. I know that this last line for the expectation value looks very complicated, but we're just basically calculating that inner product, and we're getting the projection onto the initial state. So what we're doing here, you can see we're just like basically putting the input data. We don't have our, trainable thetas. They're not here, which means that we can just plug this little part of your model and put it in your quantum circuit and save yourself, a lot of time trying to make these feature maps in a classical computer. So this is why quantum kernels were so important, and why they're so famous. Let me know how this explanation went. I know this is a very complicated topic. We're getting into like the more advanced part of the lecture series, but let me know. Yes, I have a couple of likes. Let me know if you did not understand something. Yeah.
Right. I have a couple of questions on Discord, Catalina. One is someone with a machine learning background asked that, are quantum kernels similar to the kernels we use in algorithms like state vector machine?
Support vector machine, I guess they mean.
Yeah.
Yes. So great question. Here, for example, we are using a classical support vector machine, and instead of adding a classical kernel, we will add the quantum one. So we haven't got the code for that yet, but basically we are replacing that classical kernel by this quantum one, and they will, your classical kernel will also perform the same operation. It's just that, it looked like a natural good fit to use a quantum computer for this, but they are performing the same operation. They're just a kernel. And there are different ways of making these kernels, but yes, they're performing the same operation.
Then I have another question. Yeah, thank you, Catalina. There's another question on the brief mention you had about embedding. So is there a tool set or guidelines which helps us decide which encoding or embedding techniques are better for certain data sets? Is there a general rule which can help us decide that?
The general rule would be whatever separates your data more into distinct quantum states. So that means something different for each data. So if all of your data are, angles between 0 and pi, it looks natural to use angle embedding. If all of your data are, binary bits, maybe you'll want to use a basis embedding or encoding, because it kind of has that same like mapping, which is kind of logical to my kind of binary to binary. You may have something completely different, and in that case, you might want to use an amplitude embedding. You would need to normalize it. You just set the flag for it to, Penny can normalize it for you in case it's not normalized. So amplitude embedding can also be useful. But the key here, and like the summary, would be whatever takes your data and maps it, let's say, maps it better into distinct quantum states. Like here on the right, we have a feature map that is mapping each class into distinct, regions of the space. So you would want kind of to have that same thing for choosing your embedding.
Perfect. Yeah, thanks, Catalina. I think we can move forward.
Okay, good. And if you need to pre-process your data, for example, let's say you have angles, but they're all between, in a very small space, you might have to multiply them or divide them by something to separate them more, to make it easier for your, program to succeed. So there are other kinds of kernels. In this case, for example, this is a convolution kernel. And what you're doing here is you're having an image. You're inputting different little bits of the image into a quantum circuit. So this is just a 4-qubit circuit where you have rotation. So this is an angle embedding. This is an angle embedding. You're basically changing the value of these pixels. You're plugging them into each into an angle. These probably have been divided by 256 if they're RGB, because otherwise they wouldn't be mapped in a distinctive way here, right? So this is a very appropriate question. And then you have a unitary, which will modify that data. So this will be the kernel that will modify the state. And then the output of this can be inputted into a different, a certain classical training. So what you're doing here is you're modifying this data to separate it, to make, to help the classical training work better. Basically, it's like a helper function. So this is a convolution kernel because you have a large image and you only have 4 qubits. So you're going to basically move this little by little. So you're going to be moving across the image little by little in something that is looking kind of like a convolution. We have a full demo on this, so definitely, and I'm going to share this at the end, where you can find all of the resources that have more detailed examples, all of the math, all of the images, all of the code to understand how these work in detail. But this is good to see an example of a different kind of kernel. And it turns out that this is not free. This is not like, this is going to take a lot more executions. This is for the first example, not for the convolution kernel, but for the other one. You will need a lot of evaluations for this. So it's not like you're getting better results for free. Sometimes they won't be better, and sometimes they will require more time and more executions. So what you see here is at the very bottom in the blue dotted line, you see just a simple neural net. If you use a certain like optimized variational circuit, you can get something similar to that. If you use a quantum kernel in this case, you need a lot of evaluations. So it doesn't scale very well in this case. So you'll have to be very careful about what your application is, and if you're gonna have a huge data set, you're gonna have to be careful about it. And some other variational circuit that is not as optimized, it performs even worse. So when you hear all of these comments about, how does classical compare to quantum? These are interesting images to have in your mind. even comparing quantum to quantum, you have to be careful about how optimized it is, what techniques they're using, etc. And sometimes classical, just pure classical can be better. So not because we can do it in quantum, it necessarily is better. Let's try it out in a code example, and I'm actually going to go back and show you also the answers. Some additional, sorry, a sec. I don't know. I think you're seeing the right screen. I just don't know how to make it full screen. So just give me a sec. I don't know, it doesn't show me the button for full screen. So you'll have to bear with me unless somebody knows like the specific command for that, but let me know if you don't see it well.
Yeah, we can see it in full screen. So
You can see it well. Okay. All right, good. So last time what we did is we created a small circuit. So let me go back to the circuit. Last time we created a 1 qubit circuit that had first an encoding. This is an angle encoding. I encoded one single data point into an Rx rotation. Then I created an ansatz that had 2 rotations. And I encoded 2 parameters, params 0 and params 1 here, in order to try to model a sine function. So I used a loss function and a cost function and an optimizer. And in the end, what I got is that my quantum circuit was able to model the sine function. Vardaan, I think you shared the blog post that has, the very similar code. So you can look at the blog post to get all of the details.
Yeah, the blog post has been posted on the Canvas module. So all the participants are just encouraged to view this particular blog post on the Canvas module for quantum machine learning. And yeah, if there are any questions, you can always post them on Discord.
Okay, perfect. So now, what if we change the data set? So instead of having a sine function, we're going to create a number of points, and we're going to get y equals x. This is basically a line, but with a little bit of noise, just a tiny little bit of noise. So we created a noisy line with our train and our test data, and we tried to run the same circuit. So we didn't, we used the same optimization routine. We found the best parameters for that. And when we ran it, we didn't get the right output. We got something completely different. And you can even see in the optimization, the cost is going up and down, up and down. It's not really optimizing very well. What if we try it with maybe more parameters or, a different circuit? So in this case, for example, for the ansatz, instead of having 2 parameters, I added a 3rd parameter. So one generalized rotation with 3 parameters. And it turns out that we also didn't quite make it to the straight line. So does anybody know why it worked so well for the sine function and not so well for the straight line? Can anybody make a guess?
I see some people typing on this board. So let's just give them a minute to write the answers. Archit from India comments, maybe it's not a good ansatz.
Maybe, yeah.
Answers, perhaps there are more data points.
More data points. Who else? Anybody else?
Hussein answers, there's something to do with the cost function.
Yeah. Well, it's the first answer was closer. So it turns out that with one rotation, we cannot, we cannot represent the complexity of a straight line. It turns out that our quantum circuits work a lot like Fourier series. And these are based on a combination of sine functions. So in order to represent the straight line, we would need a different ansatz that doesn't rely on a single rotation because it's too simple. It's too simple to represent the complexity of this straight line. It's more complex for a quantum computer with this specific ansatz for quantum algorithm. So this is why, in general, you would look at how others, what ansatz they have used. So for example, you can try using many more rotations. We can try it live. Let me just make sure I have, I probably need to re-import Penny or pip install Penny. Okay, it was already there. And make sure I import it. All right, it's already there. So now, oh, and I need to run my data. Sorry, I didn't run dev. Let me run this example. Well, I'm gonna recreate the data. So I'm just gonna run my device. I'm gonna run my loss and my cost functions. Oh, I'm gonna run my plotting function. This is probably not gonna work, but it's okay. And we're gonna test it in data sets. Oh, we need to import PennyLane as PMP. Or from PennyLane, import numpy as PNP. Right. Perfect. See, oh, we haven't defined the optimization routine, which is, oh, here. And I think we're gonna be ready. Here. And we need to define our quantum circuit, which we will define here. So I think now we're ready. So we've created our new keynote. And let's see, it's starting to train. Oh, this is just with a single rotation, but we can try modifying it in a sec. All right, let's see how we're doing. Should finish quickly in a couple of seconds. I think I have 100 steps, so shouldn't take very long. Let's see. Blood results. We didn't define it. I thought we had defined it. Let me just run this again down there. And we just run this plot. Import matplotlib as PLT. Import matplotlib.pyplots as PLT. All right, so this is what we had got before. Can now remove these and we can run it again. So this is what we have got. Now let's modify the ansatz. So how do we want to modify the ansatz? Who has any ideas? Maybe we're gonna create a lot of rotations. What do we think? Any guesses? Vardaan?
I see a few people typing on the start.
Okay, what ideas do we have? Maybe we can use a different answer. So let's go to Pennylane, pennylane.ai. We can go to the documentation. So here in the navigation bar at the top, you can go to the left-hand side and look at templates. Let's see what templates we have. We see many embedding templates. So here's a QAOA one I mentioned, different ones. Some of them are for photonics, so I would be careful of the ones that say displacement and squeezing. But the first couple of ones should work. I would also recommend please avoid the CV neural net layers because the CV is about continuous variables. So this is for a different kind of programming idea. One that I use a lot is strongly entangling layers, which has, these rotations with a lot of entanglement after. So what we can do is we can copy this little line of code. We'll just have to make sure that the weights have the right size. So has anybody used strongly entangling layers before? Maybe you can give me a reaction if you have. Let me see your reactions.
Yeah, sometimes we have done it,
a
but
couple of people.
right,
All right.
and some of them haven't tried it yet. So
Good that we're trying it. So here our weights are called params. And we're gonna, yes, it's called params. And we're just gonna make sure that the size of the parameters is right. So we're gonna look here in the documentation. We see that the shape depends on the number of layers that we want and the number of qubits. So I'm gonna copy this and I'm gonna paste it as well. We just had one qubit before, right? So I guess maybe we can create a new device so that we can have more qubits. How about that? We can do def equals QML.device. We're going to use default qubit.qubit. And we're going to say parse equals 4, for example. Oh, default with an A. Here we can run our new circuit so that, it's going to run later. And for our initial parameters, we're actually not going to use the ones we had before. We're going to create these as weights. So I'm going to call them init param so that everything else runs nicely. And here we called our NumPy import, call it PNP, because it's imported from Pennylane. That's it. We have 2 layers, 4 wires. Let's see. Let's see what we get. All right, it's running. So that's always good. So this is how you would generally do, when you're working on a problem you'll realize that it doesn't matter if you change your initial parameters, it doesn't matter if you change this or that, you don't get the right answer. So, it tests with the different ansatz. It's it's common to decide to add more parameters or, more layers, for example, but that has a limit. You don't, you cannot guarantee to get the right answer even after adding many different layers. But this is something we can try. While this runs, let me show you a different example about quantum kernels. I think you're seeing the right one, right? Yeah, you're seeing the right one. So here what we're doing, first, this is a nice example of a variational classifier. So this is, you also can see a demo online, where you don't only have to like classify with a straight line, you can actually have a different kind of classification that is not only a straight line. This is also based on a demo. So we're gonna use a quantum kernel, and we're gonna use it together with classical optimization. So scikit-learn is a classical package that you can use. And this is a support vector classifier. SVC stands for support vector classifier, which is gonna help us like find that split between the data. Here we first have a pre-processing of the data, loading and scaling. This is important, as I mentioned. You want your data to be mapped like very different, each data point to be mapped as a different point, very different point in your basically quantum space. Now we're creating a device. So the number of qubits will depend on the number of training data that we have for this particular example. Our device is, we're going to use default qubit with this number of qubits. Here we're measuring on the projector. So this is the same example that I showed in the presentation. We're first defining this projector, which was our initial state. We define our quantum kernel, and we're gonna find the expectation value with respect to that projector for the specific kernel. This is a test. If you do the kernel of one data point with itself, it's basically comparing how different these two vectors are. So x1 and x2 are like two vectors. So it's comparing how similar they are. And if you compare one vector with itself, you say one because they're completely similar, right? You can create something like a kernel matrix. So for data, if you have two data sets, A and B, you can kind of like get the answers, basically get the answers for the whole data set. So this was our kernel matrix does. And what you do in the support vector machine, in your support vector classifier, you simply add this keyword argument where you add your kernel matrix, which is all classical. So this kernel matrix has been calculated, based on that kernel. So the output of this kernel will give, the value for each pair of data between A and B. It's going to give you, it's going to put it together in a matrix. So if you had A on one side and B on the other side, you're going to get a matrix of that. So this is a classical matrix. This is not composed of quantum state, but of the output of running this kernel on your quantum circuit. So it's basically this helper that will help you map that data into this different space. That's what you want. And if you calculate the prediction and the accuracy, in this case, you say, okay, I got a really good output. Now it did take a lot of executions. So you can use like different methods, for example, within Penny Lane, to find the number of executions that you needed. And here we are calculating that graph that you saw, where the number of executions that you would need with a classical neural network actually is way lower than for using this kernel. So let me skip all the way to the answer. it kind of looks like a flat line, but it's not flat. It's just it's increasing, but very, very slowly. It's increasing much slower than the number of executions for your quantum kernel. So this is kind of what I wanted to show you here. I think this is still running. Oh, it's almost done. It's almost done. Maybe I can skip a little bit to. I'll skip a little bit to the end. Just a reminder, the reason why we could do all of this, and in a couple of lines of code, I could change the ansatz. It's because Penny for example, is designed for this, right? So you can use any software that you want. You're free to do that. A lot of them are open source. I always recommend that you use open source and you support open source software. But all of them have their different things that make them special. What makes Penny special is that it's designed for this hybrid programming, and that it's designed for differentiability. And hybrid means it can run together with different classical software like Torch, like JAX, like scikit-learn, and classical as well, quantum as well. Quantum, like it runs together. You can code something in Penny and then run it on IBM hardware or IonQ hardware, or Amazon Bracket with all of their hardware that they have there. It's composed, or the way you can think of these are you use quantum circuits as functions. So you put everything inside a Q node. The Q node will contain everything that is quantum. And you can actually use some classical functions like for loops, for example, there as well. I skipped to going too fast. Something that is very valuable is that we provide, a lot of education, a lot of support, a lot of training, a lot of events as well. So this is something that has real value. And the community is huge. The community is huge. I know you have a beautiful, big Womanium community. So hopefully you can also join the Xanadu and the Penny community, right? Penny our discussion forum. That's where you can ask all of your code questions. In Slack, you can chat, and Discord as well. And if you're interested in something fun, I'm gonna share. Let me share this link in the chat in case you want to explore gate emojis in your own, maybe in your own Slack, or I don't know where you would use, maybe on Discord as well. Maybe you can try them out, the gate emojis. I'll share them here in the chat, and Vardaan, maybe you can help me share them, share this link. I think it's something fun that you can always add to your different Discord, etc. Let's see, I think we got the answer right in time. So, we didn't get what we expected. It turns out that the ansatz was not what was causing the problem. Maybe it's something in the cost function. Maybe it's just we need something more complex. But this is kind of like how the process works. This is how the process would work of what you would try. After this, maybe you'll need to look into the cost function to see what is going on. But I hope this gave you an insight into the process of how you would tackle one of these problems. So just to finish, if you have any questions, let me know.
Wonderful. Thanks a lot, Catalina, for an amazing session once again.